Jethro van Ekeren from IMPA, and so he'll speak on Hodge filtrations of configuration spaces and Chiral homology. Please.
Okay, so thanks so much for the introduction and for the invitation to be here. So this is so joint work in progress with Raimondo Eluani. Which is indeed part of an ongoing project where we're trying to better understand this construction of chiral homology, which can be thought of as somehow some sort of cohomology theory for complex algebraic curves that takes coefficients in a vertex algebra, or more generally something called a chiral algebra. So what it generalizes is quite an old construction in Lie theory and algebraic geometry called conformal blocks. So I want to say briefly what conformal blocks are to kind of motivate what I'm going to say. So if we start, like in Arakawa's talk, begin with G, a simple Lie algebra. We have corresponding affine Lie algebra, which I'll write like this. And let me just take V to be some G hat module of level K. So for example, it could be precisely this vacuum module, which has a vertex algebra structure, or its quotient LK of G. And now this construction is also partly geometric. So let's also take X, some complex algebraic curve. This is more or less the same thing as a Riemann surface. Let's take little x a point. And in a neighborhood of x, we'll let t be some coordinate. And what I want to do is take x minus this point, call that x line, and consider the space of meromorphic functions. So in other words, meromorphic functions that have a pole only at this point x. Then something you can do is take some function times an element in the algebra G and consider its expansion at point x. So we get a map from this into power series with coefficients in G. And well, now we can let this act on our module for the affine algebra and consider co-invariance. Co-invariance, we'll call H0. Like that, okay? So this is a little bit like Lie algebra homology for a module in the usual sense, except that now it kind of mixes this geometric part as well. And when I said conformal blocks, that's just the dual space of the space of co-invariance. So these spaces are very much studied in algebraic geometry and in representation theory. Let me just mention, so for example, if we take X to be a torus, and it doesn't really matter what point we take, but let's just take the origin. And if we take V to be this particular level K G hat module, where K is a positive integer, then as Tom York already explained to us, the category of representations of this thing as a vertex algebra is particularly nice. And this space of conformal blocks sees rather a lot about this category. So in fact, you could say that the dimension of the space is equal to the number of irreducible, well, and without getting too involved in details, say that the space in some sense knows the characters or graded dimensions of these modules. So these spaces are important in representation theory. Well, now, as you've already begun to kind of mention the connection with vertex algebras, so let me start by saying that one can generalize this picture to the context of vertex algebras. So in fact, I want to generalize in two ways. So firstly, pass from this affine context to a general context of via vertex algebra. And secondly, we want to introduce somehow higher analogs conformal blocks. So I've written H0. The point is that there's going to be some Hn where n is greater than or equal to 0. Which are kind of higher homology groups in the same sense that co-invariance of the action of a Lie algebra on a module has higher homology groups associated. And so, perhaps to give some, well, I should be trying to answer some question in this talk, so I guess I'll say, under what conditions on V can we prove finite dimensionality, for example, of these higher chiral homology groups? Okay, so I should explain a little bit the definition, the structure. So firstly, I should say so vertex algebra is firstly a vector space. So it's then equipped with an infinite number of products. So if we have A and B and V, then we have these so-called nth products for all integers n, which we generally gather into a power series like this, which we write in short form in this way. And there should also be a so-called translation operator, which in a sense implements a derivation of these what are called quantum fields. So this should satisfy that the derivative okay, so that's the axiom. And a consequence of the axiom is that field associated to T of A is equal to this derivative. And the axiom which I'll omit is called locality. It's a kind of analog of, well, it's not really itself an analog of being a Lie algebra, but anyway. Right, so what can we do with this structure? Right, so as I said, there are infinitely many products in this algebra, but you can kind of organize them in various ways. So one thing you can do is, well, yeah, all right. Let's say we take two elements and we take some formal power series, f of z. So there's some Laurent series. And if we wanted to get a single element of V, we could apply the field A to B, but now we get something that depends on Z. Then we can multiply by our function and extract some coefficient. So canonically, we would take the residue, for example. Okay, so this is defined a map from V tensor V. But you see, because V is an algebra that involves this kind of function-valued product, in order to say what this map is, we have to tensor also with the space of functions gamma 1. So the idea is that the cohomology of this complex that I'm going to build reproduces conformal blocks in degree 0, but I'm not going to extend it to higher degrees in a more or less natural way. Okay? And that'll be more or less the definition of chiral homology. Okay, so here's degree 0, degree 1. We're going to extend it to higher degrees. So before describing the complex explicitly, let me just remark on an answer to this question which has been given in the case of degree 0 by Arakawa and Kawasetsu. So it's an old construction of Zhu that if you take a vertex algebra, divide by the subspace spanned by all -2 products of elements, equip it with a product induced by the -1 product, and the 0 product giving a bracket, then this is a Poisson algebra. Okay? So here when I write H0, I mean H0 of this complex, and with gamma I mean the ring of functions on the elliptic curve minus that. Okay? So again, I keep returning to this particular case for reasons that I won't really explain, which are that the case of conformal blocks of the torus are of particular relevance in representation theory of vertex algebras. So there are reasons to be particularly interested in this case. Proposition, and of course what I forgot to mention is the proposition is due to Arakawa. And Kawasitsu. Okay, so before describing the extension of this complex, let me make an observation do just here at this point. So if we look at the residue of a derivative of a function, the property of the residue is that the residue of a total derivative is 0. So really this is equal to minus the residue of f. We can apply the derivative to this field here and then exchange that for a t acting on A. Okay. So it would be equivalent to replace this term in this complex that I want to build with the corresponding quotient, right? Because, so here t means t acting on the first copy of v, sorry, ty, plus the derivative of such terms will go to 0 when you take the residue. Okay, and so similarly to Lie algebra homology, we want to extend this complex kind of to something that looks like a Chevalley-Eilenberg complex. Except that at the same time, in order to let some element in the vertex algebra act on another element, we also have to introduce a variable. So the nth term in this complex is going to involve not only some number of copies of v, but also an increasing number of variables in the functions that we take. So more precisely, what we should do is take, well, let me write fxn to be the configuration space, x1, x2, up to xn, such that no two of the points coincide. Okay, so this is inside the nth product of x bar. And now we could take the set of meromorphic functions on this. Global sections. And this I'll call gamma n, in analogy with gamma 1. Now, with gamma 1, I had 2 copies of V. So at gamma n, I should have n plus 1 copies. And now this detail I mentioned that you're allowed to quotient by some actions of derivatives. So I'm going to do that. All right. And one final thing. Remember that Chevalley-Eilenberg complex, well, the analogy is not quite as strict as I'm going to imply, but in the Chevalley-Eilenberg complex, you don't really take a tensor power, you take a wedge power, right? Exterior algebra. So there should be some quotient by a symmetric group action. So let me take coinvariance with respect to symmetric group action. Okay, and I won't explain exactly, but it permutes the variables of the function and simultaneously permutes the first n of these tensor factors. Call this Cn. And now we can build a complex. So D will take some by habit, I'll typically write terms in this form. So there'll be a function, then a bunch of terms, and then one that I'll call B. And it's going to send it to I less than j. So we get terms in which we let the ith term act on the jth term. Simultaneously, we should think of the variables xi and xj as coming together. And then we take a residue at this point where xi equals xj. And there should also be a collection of terms where the ith one of these guys acts on B. So you think of the final copy of V as being a module which we're taking coefficients in. And in fact, you can write down a more general definition in which you take some V module for the n plus 1th term in this factor, and everything works the same. Okay, so first remark is that this notion of chiral homology is due to Beilinson and Drinfeld. Their definition is somehow much more sophisticated than the definition I gave. They describe some equivalence between vertex algebras and Lie algebra objects in some category of D modules on round space, right, curve, and they define chiral homology as a decomposition of a bunch of derived functors. So in a sense, what I've written out is sort of an underived version. So it's not exactly the same thing as chiral homology in the sense of Behrens and Drinfeld, but it's somehow a first approximation. Also, everywhere I've used functions, when in fact really, well, as I've said here, what I've written works for elliptic curves. For other algebraic varieties, one needs to do something a little bit more sophisticated, but morally the same thing. Okay, so the next comment I want to make the next comment I want to make is that using this relation, one can always transform, so if you have some term here in which the function is a derivative of some other function, you can use this relation here to transfer the derivative onto the, one of the copies of V. So basically, you have a surjection of this sort. We have just taken this ring of functions and divided by all derivatives. But now on the other hand, using the theory of D modules, this is just a presentation of the top de Rham cohomology of the variety fxn. So what one has is so in a sense, this reduction has got us down to, well, something that's still infinite dimensional, but it's a finite dimensional space tensored with a bunch of copies of V. And all the terms in our complex look like this. Okay, so I want to be fairly concrete and specialized to this case of the elliptic curve, the torus. So the Betti numbers, the first couple of fn's go as follows. So we have n, 1, 2, 3. The x itself is Betti numbers of 1, 2, and 1, Betti numbers of a torus. When you puncture it, remove this point, that just kills the top Betti number. So degree 0, 1, 2. Betti numbers look like this, 1 and 2. Betti numbers of fx bar 2 are as follows. And these numbers get pretty complicated. And in fact, as far as I know, there's no general known formula for these Betti numbers. What does exist as a way to compute them, so let me remark here, so these, this 2 here corresponds, if you think of this as de Rham cohomology, the class dz and dz bar, which are two global one forms on this torus. So Taro explained a very nice paper how you can find a presentation for the Lorentz spectral sequence which computes these Betti numbers in general. So the basic idea, the cohomology ring is generated by n copies of the cohomology ring of the underlying variety X prime and some generators that he calls Gij, where I is less than j. The best way to describe it is like so. So, well, what he explains really is the structure of the second page in this Lorentz spectral sequence. So you have on the bottom row kind of the cohomology of X bar itself n times. So let me take n equals 2, for example. So I claim that the answer is 1, 4, 5, the Betti numbers. So what it does is take 2 copies of the cohomology of X bar. So that's this ring tensored with itself. So the Betti numbers are 1, 4, and 4. 1, 4, and 4. Two times. And then in degree 1 here, there's Gij. I think, okay, it's working. Comes with a copy of the cohomology of X itself. So we get one guy here and 2 guys here. And as I say, this is the E2 page in some spectral sequence. So there's also a connecting morphism here. And when you take the cohomology with respect to this connecting morphism, it turns out that this element does not go to 0, so it disappears, and it lands here and kills some element here. So the next page looks like 1, 4, and 3, and there's nothing here, and there's 2 here. And then to get the total cohomology, you have to take diagonals. And that's how we get our 1, 4, and 2 plus 5. Okay? As written here. And so there's a similar procedure for all values of n. So I'm going quite slow here. I won't explain in too much detail, but each of the cohomology groups, complex algebraic variety, carries this natural decreasing filtration called the Hodge filtration, where GP HK equals, let's just say in quotes, Okay, so presenting cohomology in terms of differential forms, if we're looking at kth cohomology, we should have k forms in total. And if we say that at least span by forms, maybe S where the number of holomorphic forms is at least p. Okay, so this is a decreasing filtration. So for example, over here, dz bar is in G0 because there's no holomorphic forms, and dz is in G1. Okay, so if we unwind definitions in this complex, if we look at the class corresponding to dz times a times b, and look at its image in degree 0, we just get the zero product of A and B. Okay? So the next question is, what does the other generator of cohomology go to? And this is kind of trickier because we now have to think of this form not as an anti-holomorphic form, but somehow in terms of a space of meromorphic functions. So if you consider, so I'm going to consider the following function. Z minus, well, Z bar minus Z. So it's a function of Z. I'm trying to construct something like an elliptic function. So this is obviously one periodic, simply because it is. But what about if, we increase the argument by tau? Well, this function as it stands is going to increase by tau bar minus tau. So actually, let me renormalize like this. Then this function becomes quasi-periodic in the tau direction, right? So this is an example of a quasi-elliptic function. It's not quite elliptic. Now there's another, but it's not holomorphic. On the other hand, there is a holomorphic quasi-elliptic function similar to this. It's called the Weierstrass zeta function. Of z, which has an explicit formula, 1 over z minus sum of, it's kind of complicated. There's these so-called Eisenstein series that appear and powers of z. Anyway, this has the property that it's again one periodic. And up to a normalization, there's the same kind of periodicity in the tau direction. So if we take an appropriate linear combination of these two functions, we get something which is really elliptic. So this function is elliptic. So since it's a global function, so if I take the differential of this, which means that in cohomology, this class is up to some normalization factors that don't really matter, given by minus derivative of zeta. So the answer then is that the image here should be given by taking a residue against the Weierstrass P function. So it looks like A minus 2, B plus, well, G2 times A0, B plus blah, blah, blah. This whole part is very complicated. But the way to deal with it is to introduce a filtration. 15 minutes. So let's take an increasing filtration on our vertex algebra V, the property that if I take any nth product of two parts, then G, well, it lies in GP plus Q. And we want to have it that if n happens to be greater than 0, then it actually falls down 1 in the filtration. Okay? So an example of such a filtration is if you choose a set of strong generators, the vertex algebra, and take corresponding standard filtration. So for those who don't know, it's analogous to PBW filtration in enveloping algebra, early algebra. So think of something like a PBW filtration. Now returning to complex, I want to define an increasing filtration on the complex. So I'll take same equal. Okay, so we combine the two filtrations in the following way. Now, why have I done it precisely like this? It's for the following reason. Okay, so now our anti-holomorphic form goes to what you would hope for, right? We get A minus 2 product B, and then all of these terms, because they're positive nth products, they go lower in the filtration, and so they disappear in the associated graded. But at the same time, I don't want to apply that associated graded in a naive way, because I want to preserve this A0B here, right? And so if I'm going to kill A0B here and not kill A0B here, then I need to adjust the weight of this term to be different than the weight of this term. And that's what the Hodge filtration does. And if we look at the zeroth homology of the associated graded, we get exactly this. Did I mention that this was the so-called zeroth Poisson homology of our V? But anyway, the point is, if you look at the homology of an associated graded, that gives an upper bound on the size of the homology of the actual complex. And so we recover, in this case, this result of Arakawa-Kawasetsu saying that if this is finite dimensional, then our original conformal blocks were finite dimensional. But yeah, as I'm saying, this quotient here is just the zeroth so-called Poisson homology. So let me just briefly say what that is. In general, well, yeah, I will get to that. Okay, so yeah, now the next step is to extend this to higher homological degrees. So let's write A, not all the algebras, GR. Right, so let's write A for the associated gradient of V with respect to this increasing filtration. So just remark that with the -1 product as product, and with T, well, T will act as a derivation of this product, and in this way it becomes a commutative algebra with derivation. Okay, so our complex now starts to look something like a copy of A in degree 0. In degree 1, we have 2 copies of A, but one of them is multiplied by dz bar, and the other by dz. As I mentioned, these two maps are the -2 product and the 0 product. And then in the next degree, well, remembering that the Betti space is 5, there are going to be 5 copies of A cubed in this column. So 2 of them are here. I won't bother writing out all the corresponding differential forms. Let me write, so remembering that dz bar corresponds to P, this is basically 2 copies of P in some sense. Here's a copy of P and also that strange generator that appeared because of the spectral sequence called G. Here there are 2 copies again. And finally down here, there's just an A cubed. Also have a map here. There's also, well, yeah, there's also a map here. Okay, so the image of these terms here looks like A minus 2B. So we have 2 copies of A, and we have an image spanned by things like A minus 2B tensor C, and terms that look like A tensor B minus 2C. These come from, well, I wrote P here, but it could be P of x1 or P of x2. And the images of those 2 terms give these 2 terms. The image of the G term gives so if you look at the quotient here by these terms, what you see, well, first, quotienting by these sorts of terms, reduce the quotient from A tensor A to RV tensor RV, right? In terms of the form A minus 2B, okay? So we get a quotient of our V tensor RV. Wait, is it that time or? Oh. Huh? 5 minutes? Okay. Yeah, well, as I say, if you quotient by these terms, this becomes RV tensor RV. And then when you quotient by this sort of term, well, if you stare at it, you see this is giving the definition of Kähler differentials. So what we have here really is omega of RV. And in the next degree down, I didn't draw it, but you have terms analogous to this that kill off all the -2 products and all the factors, and all the 3 factors of A here. And you have terms of the form Gij, which kill off these corresponding terms. Remembering that you also have to you have to symmetrize. What you get here is the second wedge power of omega RV, and so forth. And now what do we do next? So we've already taken the associated graded with respect to a filtration. You'll observe that this complex now acquires another filtration, because the second row here maps into the top row, but the top row doesn't map back down to the second row. So it's a subcomplex. So you have a subcomplex, and then another subcomplex, and as you include more and more rows, you get an increasing filtration. So what you can do is take associated graded with respect to that filtration. This differential disappears. We get cohomology, which is something here, something. With some maps, the next page in the spectral sequence, maps going diagonally reappear. So we get here ADX. Again, if you unwind the definition, you see that it turns into the Poisson bracket of A with X. And here you get A dx dy goes to, I'll probably get the signs wrong, but something like this. Okay, so yeah, the result I wanted to present is that after doing this calculation on this leading diagonal, we get exactly a copy of the so-called Lishnierovitz complex, which computes so-called Poisson homology of this Poisson algebra RV. And I optimistically conjecture that all the question marks in the rest of this complex actually disappear. So I'll stop there.
Thank you very much. Questions, please, comments?
So you conjecture that the Chiral homology is the same also?
Well, perhaps. There are several caveats, because firstly, we're not really computing Chiral homology in the sense of Bellingson and Drinfeld. It's homology of a complex which is somehow underived Chiral homology in a certain sense. So for H1, the homology of our complex coincides with Chiral homology in the sense of Bellingson and Drinfeld. But already for H2, there's some term which in principle could appear that would cause a difference between the two. So I'm not sure. And secondly, whether the cohomology of our complex is given by Poisson homology, I suppose it's true. I'm slightly wary because it's two associated gradients, one after the other. So certainly it should compute the so I guess I conjecture that the homology of this associated gradient is given by this Poisson homology, but there could occur further corrections after that, I think. But somehow the point is we believe that this gives a control on the size of the Chiral homology. So we believe that any condition that guaranteed finite dimensionality of these Poisson homology groups conjecturally would guarantee finite dimensionality of Chiral homology.